let's try to do this a little bit more. We'll do this in a very trivial way, right? So let's look at the determinant of a 2 by 2 matrix. So let's do this one. Okay, so this is a very trivial, and we know the determinant of this matrix is equal to A11, A22 minus A12, A21. Okay, and I'm going to write this as okay. Now let's look at the first term. This corresponds to the permutation. We can think of the associated permutation pi that sends 1 to 1 and 2 to 2. And the second term we can think of as an associated permutation that sends 1 to 2 and therefore 2 to 1. Okay? And so if we now look at the permutation associated here and compared up there, what we're saying is take 1 maps to 1, so we write down A11. Take 2 maps to 2, write down A22. Oh, that should be A22, sorry. And take their product. That's that term inside the thing up there. Okay, so that's one term. Add to this another permutation. This is the other permutation you have, 1 to 2 and 2 to 1, and write that down. And here there's a -1 because every permutation has a notion of a sign. Basically, it's the number of how do I say this? The sign of a permutation. What is the easiest way to explain what that means? It's a way that measures essentially sort of. I've forgotten the definition of sign of permutation. Hold on. It's kind of measure the number of reversals. I'm trying to figure out which way to see this. But every permutation has a sign associated with it. And it's a well-defined thing for any permutation. It has nothing to do with the matrix. And so in this case, the permutation is -1, and that's why you get this times 1 plus this times -1, and then you get that term up there. And if you can write this out, what the determinant of a 3 by 3 matrix looks like, it'll look exactly like this. Now you have permutations on 3 things. So there are, how many permutations can you have of 3 elements? Six. So there'll be 6 terms if you write them down, right? And again, you can see why there'll be 6 because there's 2 for every 2 by 2, and then there's 1 row and then 3. So for every row, for the first row, you take the first element multiplied by a 2 by 2 determinant, second element by a 2 by 2 determinant, third element by a 2 by 2 determinant, and that'll give you 6 terms, and there'll be 1 for each permutation. And each of them will involve products of this kind. Okay. So this is a well-known sort of property of the determinant that you can write it in this form. Notice that there are exponentially many terms in this expression, right? Because the number of permutations on n elements is n factorial, right? Which is 2 to the n log n. So what you don't want to do, I mean, if I said, oh, G has a perfect matching if Q is identically non-zero, one solution is, okay, let me just write down this determinant explicitly and see if it's identically non-zero. You can't do that because it has exponentially many terms. You cannot write this down explicitly, okay? But what I can hope to do is evaluate it. And there are ways to evaluate a polynomial efficiently, right? And then hope that I can do something reasonable there. And so, if we believe, therefore, that the determinant can be written this way, can we use this to prove that fact? Well, here's one way to think about this. That term, remember, each term in that expression, in the summation, has unique variables in it. None of the variables repeat, right? Because every well, each variable appears only one in each term anyway, right? For each of these expressions, because there's only I and pi I, so permutation. So suppose that G has a perfect matching. If G has a perfect matching, that means there is a matching of left-hand side to right-hand side with edges, right? So that there's an edge from something here to something here, there's an edge from something here to something here, and so on. But what is that? That is a permutation. If there's a perfect matching in a bipartite graph, you're basically saying that the first element here, U1, goes to V5, U2 goes to V1, and so on. And that has to be a permutation because no two things are going to the same thing. If that's a permutation, then for that particular choice of permutation, all these entries will be 1 because there's actually an edge. And if all those entries are 1, if all those entries exist, there's an xij there, you get a term there saying xi, pi1, xi2, pi2, and so on. Which means it's non-zero. Which means that you have a term that's non-zero, which means your polynomial is non-zero. So if G has a perfect matching, you can identify at least one term in your expression that's going to be non-zero because you have variables for those edges, and you will get a non-zero expression. Okay. Conversely, right? So we've proven that if G is if G has a perfect matching, then this polynomial is going to be non-zero. So what we have to show then is that if that polynomial is 0, then G cannot have a perfect matching, right? So if that polynomial is 0, going backwards, then because all of these are individual variables, each of those terms has to be 0. If each of those terms is 0, each of those terms corresponds to one possible way of assigning elements on one side of the graph to elements on the other side of the graph. And if each of them is 0, that means in each possible way of assigning, some edge is missing. It's like we've tried to find a perfect matching. We've looked over all possible ways of matching left to right, and there's always one edge missing, which means G cannot have a perfect matching. So I have proved now that G has a perfect matching if and only if this polynomial is not identically 0. Which means then that if I want to find out if a graph is a perfect matching, a bipartite graph, I have to do identity testing on that polynomial, which is something we've already seen. Now in this particular case, this is not as efficient as actually computing a matching. So this is not the best algorithm for this. But it gets used in other contexts. And there's a way to modify this procedure, which may or may not be on homework. I have to think about whether it's a good question or not. That you can modify this for the case when the graph is not bipartite. You change the way you encode your matrix and you can see it. Okay, so the basic idea again, just like before, is take your problem, figure out a way to make it so that what you're really doing is testing if a polynomial is 0 or not, identical, and then invoke our technique for checking if a polynomial is identical 0 by randomly sampling it. Okay. All right. Yeah.
Before we scroll away, could you walk us through the notation there for that determine a summation?
Yeah. So what it's saying, it's a sum over permutations, all possible permutations. Sn is the symmetric group on n vertices. So basically, sum over all permutations of n things. Each permutation is a mapping from 1 through n to 1 through n. Right? For each of those permutations, you have to compute that product, and that product says take 1, look at its thing it's matched to in the permutation, which is pi of 1. Look at the entry of the matrix A corresponding to that coordinates, and take that whatever is there, which will be some variable or 0. So in this case, I had A11, A12, A21, A22. The first permutation was 1 goes to 1, 2 goes to 2. So I take A1 comma pi of 1, which is 1, 1, times 2 comma pi of 2, which is 2, 2. Multiply them together. That's one permutation. That's a one term. Then do this for the next one, and the next one, and the next one. Add them all.
And the SGN is the sign for me.
Yeah. So I'm sorry. It's like I should have figured this out. This is something that you know, but you don't know. Yeah.
Like what is things until you have to teach them.
Yeah, it's like I use it all the time, and if once I look at it, I'll say, oh yeah, of course that's what it means.
Like for every reverse numbers, you put a minus 1 there.
It's something like that. So
there's 1, 2, 1 there, right?
So let me. There's a red there. Yeah. So this. Okay. So let me. Right. So good. I will write it down. So inversions are when think of this as being an ordered set. If something goes to something bigger, you're fine. If something goes to something backwards, you're wrong. It's off. This has no inversions. Everything's kind of nice. This has one inversion. 1 going to 2, and then 2 going back to 1. So the sign of this permutation is minus 1 to the 1. Which is minus 1. This is minus 1 to the 0. It's also called the parity of permutation. So you get things called even permutations, where the number of inversions is even. And there are odd permutations, the number of inversions is odd, and that corresponds to this. So that's what it is. As always, these things have much sort of deeper structure the further down you go. But for now, this is finding there's a deeper connection with group theory and stuff like this. Okay. So again, this is a very esoteric example. And so what I want to take away from this is not the weirdness of the sign of permutation with determinants, but the idea that you can take a problem, in this case, finding a graph of perfect matching, and there are ways that it's a design strategy to try and convert that question into the question of whether a certain polynomial is non-zero or not. Because once you convert that other question into the question of whether a polynomial is non-zero or not identically, then we have randomized tools to check. And it turns out this is a very, very deep idea. The idea that you can convert a question into whether a polynomial is non-zero, it shows up in well, everywhere. I mean, literally, just every single place you're dealing with some kind of question answering problem, where you want to ask a question and get an answer and verify it, you need some trick like this. I've used this in my work. People have used this in all kinds of very amazing papers over the years. It's a very powerful. All right, we're going to do one last example of this whole algebraic method in fingerprinting as a way of illustrating how randomness works, and then we'll sort of step back and take a bigger picture. So I'm going to do some more fingerprinting. And this is a very interesting sort of puzzle that again comes up a lot in sort of a big data set. So imagine that you have, as always, if you've ever done anything with cryptography or with security, you have Alice and Bob. Pairs, right? And Alice has a string, we'll call it A, which is an n-bit string. And Bob has a string, B, which ends with M. Okay? And among the most basic things they might want to know is, hey, do we have the same string? So think of this bits. Do we have the same thing? And of course, the easiest way to do this is Alice just says, hey, here's my string. Take a look at it. Let me know what you think. Okay. And this will require Alice to communicate with Bob. Okay. So Alice will send over these bits to the verification, and then Bob will send, maybe one bit back, saying yes or no. This takes, n or n plus 1 bits of communication. Can I do this any better? Can I speed up this process, especially if n is something that's very big? N could be, for example, A could be an entire database. I have an entire database of stuff. B is an entire database. I want to know if this. I want to check if two things are similar or the same without having to look at them. Because they're big. Essentially, if you think about it, every time we take someone's fingerprint, we're saying that there's a little thing here that encodes everything about us. And that's enough to identify this in some unique way. Is there a fingerprint we can construct so that Alice does not have to send all that information to Bob and can send a very small fingerprint and be sure that whatever answer is given is going to be the correct answer? And of course, since we're collapsing things down, we're going to have some error, probability of this happening, or some error, and we'd like to make it a randomized algorithm with a small amount of it. And once again, sort of polynomials will rear their, hopefully not too ugly heads, and we can sort of think about what it is. Okay. And so here's a trick. It's a beautiful trick. And here's how it works. We can think of Alice's bit string A as a polynomial. How? Well, we can think of Alice's bits as coefficients of a polynomial. So, in particular, we can write it this way. We can think of a polynomial associated right? So I mean, this is how you would do it if you thought of the binary A as a number and writing it in binary form, in this case base Z form. Right? If you think of Z as 2, this is just a way of thinking of A as a bit string and looking at the number encoded by the bit string. So there's nothing particularly special about it. The -1 is just because I'm counting it from 1 through n, but I want powers from 0 to n. Right? And you can do the same thing for B. Right? So now instead of 2 bit strings, I have 2 polynomials. Doesn't really help us very much. But what is the question I want to ask myself? What is the question I'm really asking? I want to know if these 2 polynomials are the same or not. If these 2 polynomials are the same, then the bit strings are the same. If these 2 polynomials are different, then the polynomials are different. Right? So we want to check if A is equal to B, or A of C is equal to B of C. Another way of saying this is that we want to check if A of C minus B of C is 0. Which sounds like something we know how to do, which is a polynomial. But let's do something a little bit different here. Okay? So the little bit different thing we're going to do is, normally what we would do in this case is, we would try to evaluate both polynomials at a random point. And we'd look at the random value and see the same. So A would have to choose a random value. A would evaluate A of C at some random value, would send that random value and the random string to B. B would do the same thing, right? And then check if the answer is the same. And you can do that. But let's do something a little bit different. Let's compute A of 2 and B of 2. Unfortunately, Z looks like 2. Right, which is equal to. So this is really treating AI like a binary string. And you can think of A and B as bits. It's particularly convenient to do it. Right? These are actual numbers. Right? A of 2 and B of 2 are numbers. And then we do something very interesting. We pick okay? And then compute okay? And then send that to me. And we do the same thing. We takes B of 2, computes B of 2 mod B, and compares it to A of 2 mod B. And again, same thing. If they're equal, says they're equal. If they're not equal, says they're not equal. Okay? Yeah? So is the strategy clear? They pick a random number prime, the random prime, and they agree on the random prime. And then or another way of saying this, we pick A picks a prime and sends the information to B. And then computes A of 2 mod B, sends it to B, and then so on. So let's ask ourselves the following question first of all. How many bits is A going to send? How many bits does A need to send in this case compared to in the previous case? In the previous case, you said, bits over, right? In this case, how many bits will A send over? A is sending A of 2 mod B. To figure out how many bits you need to figure out how big a number that can be. How big a number can A of 2 mod B be? So how many bits would you need? Sorry?
The number of bits we use.
How much is that? Log B. Right? So the number of bits A sends over is log P. So as long as I can make sure that log p is much less than n, I win. I've sent many qubits. Just in terms of efficiency of sending bits. There's of course the issue whether this is incorrect. And where could this go wrong? What could go wrong? So I'm comparing not A2 and B2, but I'm comparing A of A2 mod B and B2 mod B. Yeah.
You could have some weird collision.
You could have some weird collision, right? When you're essentially hashing. When you hash things down, you could have a weird collision somewhere. So things could look like they're equal when they're not. If you remember before, we didn't have that problem, right? If things were not equal, they were not equal. Right? If a polynomial was not zero, it was non-zero. Okay. Oh, sorry. Well, no. Polynomial was 0 to 0. If it was non-zero, there was some doubt that it would look like it's 0. Here, if they are not the same, you might accidentally declare them to be the same. If they are the same, you have no problems. It's just like, you agree? Okay. So then we have to figure out what is the chance that they will collide. Which means we have to figure out what is the probability that if I take a random prime number and do A of 2, which is a fixed number. So rather than saying take a polynomial and evaluate a random point in the field, I'm saying take a fixed value and choose a random field. Because P defines a random field and evaluate it in that random field. And now we want to know what the probability of this happening is, what the probability of collision is. So let's try to figure that out. So is the question clear? Our goal is to figure out, to find the probability that A of 2 mod P is equal to B of 2 mod P, given that A is not equal to B. Just like before, there's no sense in worrying about what happens when A is equal to B. That's a good case. We only need to worry about the case when A is not equal to B, and this is giving us a false answer. Okay? And here the randomness is coming not from evaluations, but from the choice of P. That's where the randomness is coming from in the output. Okay? All right. So let's figure this out. So here's the claim. So let, as before, so let C is equal to A minus B. And we know C is not true. When will that bad event happen? That bad event will happen if, so A2 mod P is equal to B2 mod P. Right? So here A, by the way, is, you should be careful, this is A of 2, and this is B of 2. Actually, value. So A of 2 mod P is equal to B of 2 mod B is the event, which corresponds to C right? Because if they're both equal, the difference is going to be 0 mod P, which means that P divides C. So what we're saying is we have some arbitrary number C that just came up because we have A of 2 and B of 2 take the difference. And we're picking a random prime number and we're asking, what is the probability that a random prime number chosen in some range divides C? So for example, suppose your number is 27, right? And you choose your prime number in some range, which you have to decide to choose from. What is the probability you pick 3? Your prime number is, I don't know, if your number C is, 86, which is 43 times 2. What is the probability you pick either 2 or 43? Right? So the first thing to, so this is only going to work. So now that we have a bit of intuition about randomized algorithms, to work, this needs to be very rare. Right? This event should happen very rarely. This event happens rarely if there are very few numbers, prime numbers that divide C. So we have to have some way of saying that, look, if I have a number, the number of primes that divide it are not that many. There cannot be that many primes that divide it. So if I give you a number and ask you how many distinct prime factors does it have? Right. So in other words, if it's 27, it has one prime factor. 3. How many what do you think would be the answer to this question? So I give you a number and I think, okay, how many prime factors might you have? Because all the prime factors multiply together to get the number, right? So that's sort of a helpful insight. If all those prime factors are multiplied together to get a number, each prime factor is at least how big? At least 2, right? So if I have any number n, so claim the number of distinct prime factors of n is at most log n. Why? Because each prime factor is at least 2. If I have k prime factors, the value of the number must be at least 2 to the k. It could be much more. So the number of prime factors, just reversing this argument, can be at most log n. Okay. So that's a good thing, right? What we're saying is, okay, the prime numbers that can divide n, they're small compared to n. They're not that many. If you think of sampling from 1 through n, the probability of something being picked as a prime number is going to be very small. So that seems like a good thing. Okay. So let's hold that thought for a second. Another thing that you may not know is the number of prime numbers less than equal to k. Okay, so we'll denote this as pi of k. Sorry, pi shows up on one. So we know that pi of k asymptotically, you know what this is? What's a fraction of prime numbers less than the range from 1 to k? If you know it, you know it. If you don't know it, you don't know. It's not something that you can infer in 2 minutes in class. It's It's like a general knowledge quiz question. If you've never seen this before, there's something like k over log k. Okay. So it's quite a large number actually in general. Okay. So these two facts together is what we're going to use. In particular, okay. So what is let me ask you the first question. What is the range of values of A2 and B2? How big can AF2 be? So remember what AF2 was? To sigma AI2 to the I minus 1 for n bits. So how big could AF2 be? Sorry?
Less than equal to 2 to the power 9.
2 to the power n, sorry. Yeah, n bits, right? Yeah, right, that's right. Same way. So we know that A2 and B2, and therefore C2, and therefore C, are less than equal to 2 to the n. Right? Okay. And then what we're going to do is we're going to choose some threshold, which is roughly like log of 2 to the n, which is roughly n. So when I say roughly, I mean somewhere above that, but not too much above that. So maybe like say between n and 2n. Another fact about prime numbers: if you take any number k and take 2k, there's always a prime number between k for any value of k. This is what's called Bertrand's postulate. So it's proven many decades ago. So it's just a fun fact. So you choose some number which is around the log of 2 to the n, so roughly around n. We know that the number of prime numbers less than equal to tau is roughly tau divided by log tau from this claim. So there are lots of prime numbers there. Pick one of them at random. So pick a random prime. Okay. And now we can ask ourselves, what is the probability that A of 2 mod P is equal to B of 2 mod P, given that A of 2 is not equal to B of 2, right? What is this probably going to be? This probability is going to be something like, let's think about this. We've chosen some random prime number less than tau, right? And there are pi of tau many many prime numbers to pick. So that's our pool. Oh, sorry. Okay. That's the pool numbers we're picking. All prime numbers less than tau. That's what we're picking there. How many of them could potentially divide C? Well, remember we just said this. The number of distinct prime factors of any number is less than log of the value of the number. So the number of prime factors of C is at most n. Okay? Right? So this number is going to be less than equal to the potential prime factors of C divided by the pool of prime numbers we chose this from. And this is going to be equal to something like n times over tau times log tau. Now we haven't really specified what tau needs to be. We just said, I want it kind of to be in the n range. But now we can be very specific. This is the probability of error. We want to make sure this number is very small, right? So we want pi of tau to be a lot bigger than n. And so what we do is we pick tau to be something like 1 over delta n log n over delta. Okay. And if we substitute that in there, what do we get? We get that the probability of error is going to be roughly something like n log 1 over delta n log n over delta, right, divided by n over delta log okay. We simplify this expression. This becomes delta times log of n over delta plus log of n over delta divided by log of n over delta, right? Which is basically done. Think about this expression here. As delta gets very, very small, basically this term dominates that term. This becomes 1. So becoming very big. Some of these things you have to kind of tweak the choice of thing a little bit. So the way I would look at this expression here, and I'm going to sort of copy this out here. Is to say that The key idea here is that you have a term for the probability of error, and you want this to be more than n, but not much more. And this actually reflects sort of some competing interests here. We want the probability of error to be very small, so we want to make sure this number is very small, which makes this big. We want to make sure it's more than n, so that this whole thing gets to be, this cancels out the n on top, right? So you need these two terms here. Okay. The problem is that you can't make it too big. What happens if you make tau too big in terms of the way the algorithm works? The way to ask this question is, we said that we send log p bits over, right? So as p gets bigger, the number of bits we need to send gets bigger. But p is between 1 and tau. We chose it at random. So it could be as big as tau. So the bigger tau gets, the bigger p gets, or potentially, the bigger p gets, the more bits you have to send. So efficiency consideration is telling us you can't make it too big. Probability consideration is saying you have to make it big enough. And this point where they balance is somewhere roughly around n over delta. If you don't want to think about this, you don't have to right now. This is kind of an extra term, basically like a noise term. This allows us to basically, just gives us a bit more oomph for our problem. But this is really what's going on. And so what this means is that since tau is roughly n over delta with an extra term there, the number of bits you are now sending is log of tau, which is log of n, or log of n over delta. We have delta as a very tiny constant. So instead of sending n bits, so this means instead of sending n bits over, which our deterministic strategy would have required us to do, we are sending log n bits over. We made an exponential improvement in the amount of information you can send just by allowing us to be fingerprinting. Moreover, if you think of these fingerprints, you can think of this as a hash function. Right? I choose a random prime. I took AF2 and computed AF2 mod p. I can store AF2 mod p with Alice. Bob can store BF2 mod p. In general, if I have a database, I can store every entry mod p. What I've stored is a database of fingerprints. And those fingerprints can be compared just like the original things were being compared. Just like the fingerprint. And that's why this is called a fingerprint, and that's why you get this power. That if you're willing to tolerate a certain amount of collision error that comes from hashing, then you get the power of compressing it down quite a lot. Exponentially. And that again is the power of randomness. And this is again something you could not have done deterministically. Right? You couldn't have chosen a prime number deterministically. Because for any fixed prime number, there will be A and B that will mess it up. Right? For any prime number, I can find two things that will collide. Because I just make sure A and B are such that A minus P divides P. The fact that I chose P at random means this can't happen. So it's like the adversary is trying to defeat you, but it doesn't know what you're going to choose for the prime number. So it has to choose A and B first in some sense. And that's why this whole process works. That's why pretty much all of randomness works. You get to choose the randomness without the adversary essentially seeing what you're doing. And there are certain cases where that's not true, but for now, let's say the first approximation is true. Okay. Any questions about what I just did here? What the process looks like? Remember, so the overall algorithm is what? The overall algorithm is exactly this. Interpret your bits as coefficients of a polynomial, evaluate the polynomial, or rather, think of your coefficients as in a binary encoding of a number, right? Take that number mod p for a random prime number and send it across. Compare the two fingerprints and declare if they're yes or no, if they're code the same. That's the algorithm, that's all it does. Everything else is the proof that says that this is going to work by looking at the properties of random prime numbers. Yes?
Was looking at the proof.
Yeah.
So, where does delta come from? What's the
Delta so think of this as a design problem. I want to design a fingerprinting scheme where my probability of making a mistake is 0.001.
Okay.
That's delta. So delta is a parameter that I plug into my scheme to design. If I want a really small delta, I'm going to need more bits. If I'm okay with a very large delta, I can use fewer bits. It's a knob that I, as the algorithm designer, have under my control. So delta is a free parameter. It's controlled and controls the space and the probability of error. So it's a trade-off. Because remember, the actual space usage is really something like log of n over delta, low order terms. And this is always going to be the case in randomized algorithms, that the error parameter is a knob, but as you change that knob, it affects either the time because of amplification, or it affects the space because of repetition. Any other questions?
In this case, since it's not much time-consuming process, we can afford to make delta a bit larger and then use the amplification, right? Because the process of calculating the mod p of a number is not expensive. So, so I was thinking like one can afford to have a bigger.
So here's the question: is it better to choose a big delta and do amplification, or to choose a small delta and use a longer prime? You have to do the calculation. See, it depends. It's not always the case that amplification is better. And that's why a lot of the ingenuity in randomized algorithms comes down to: do I want to do something with an okay probability of error and amplify it, or do I want to kind of bake the amplification into a cleverer way of designing the processes? Sometimes it's better to do the amplification. Sometimes it's better to bake it. In the case of the min cut, we had this very simple procedure, just contracting edges that have a probability of success of 1 over n squared. We changed the process to get a probability of error of 1 over log n, or success of 1 over log n, which then allowed us to amplify more efficiently. So in that case, baking the probability into the design was better. Maybe here as well. For every problem, it might be different. So there's lots and lots of cleverness about how you do this. In fact, there's lots of cleverness about making sure you don't need too many random bits. So getting random bits is not a free resource. You have to invoke some pseudorandom generator. There's some quality in randomness. So if you can use as few random bits as possible, you're happy. So there are procedures that say, okay, is there a way to generate bits that are kind of random and random enough for my problem, but don't need to be truly random? And there's a whole sort of set of work around what's called pseudo-randomness and pseudo-random generators. It's very, very beautiful work. So there's a lot of more things I'm hiding that I'm not really talking about here, but they all involve thinking of randomness as a resource, just like time and space, that you can play with. So just like with time and space, with more space I might need less time, or with more time I might need less space. Now you have a third dimension. So okay, with more randomness, maybe I need less time, but I need more space, and now you have a whole spectrum of solutions. Depending on your application, what you care about, you might choose a different point. And in fact, it's more than just random bits, you also have probability errors. Now we have, instead of designing an algorithm worrying about how fast it is, when you design an algorithm, you might say, well, time, space, randomness, random bits, error probability. And although I didn't harp on it here, communication. For large data problems, especially if you're communicating between cores, minimizing the amount of communication corresponds to minimizing energy, which is something you really want in high performance computing. So there's a lot of different dimensions to your design process, and depending on what you want, you might choose a different point on the spectrum. And the way we talk about amplification, you can think of as a way of moving between one and the other, as a trade-off with a knob. All right. I'm over time for now, so I will stop. And I'll see you all on Monday. So I apologize for the grading thing. Actually, the assignments were graded. We'd already finished it, and they were muted. So I had to unmute them, and so I unmuted them, and then suddenly they all appeared like this. And so that's what happened. And please come to us with questions if you have any questions about the grading. I think most people did pretty well if I look at the scores. So I think, I doubt. Generally, people don't have questions, they do well. So we'll see. But don't rock the boat, don't ask anything.